Hello. So today we are right at the end of our solutions unit. This video is going to go over molarity and molality calculations. So what that is, we're talking about the concentration of solutions. All right. So you have some pictures over on the side that really show you a nice, like especially this one up here and up here. It's colored so you can see the difference. Concentrations of a solution is going to be how much solute you have in a given amount of solvent. Okay, so remember, solute is what is being dissolved. So usually the smaller amount, it's usually a solid. And then the solvent is what is doing the dissolving. It's the dissolving medium, usually a liquid, and oftentimes it'll be water is a really good solvent. So you'll see water as a solvent most of the time. So not all the time though. So solutions, depending on their concentration, are going to be referred to as dilute or concentrated based off of how much solute has been dissolved. And that term can be expressed in terms of molarity and molality. Molarity is what you're going to see most often because it's measured in a volume of liquid, and molality you'll see occasionally, and that's measured in kilograms. So if you were looking at this grouping, you would obviously say this one is dilute and this is very concentrated. You also get the terms of unsaturated, saturated, and supersaturated within this as well. This one down here shows you different concentrations of hydrochloric acid. So it's kind of hard to see in this picture, but you can see that this one's a 1 molar solution of hydrochloric acid. This one I believe is 3, and this one looks like it says 4. So as you go up, this one is 4 times as concentrated as the first one. So when we're working with these solutions in lab, these concentrations of acids and bases, the higher the molar, the higher the molarity on it, the more concentrated it's going to be, which means that any effects it could have are also intensified. So if this is corrosive to your skin at 1 molar, that reaction would happen more quickly at 4 molar because there's more of the hydrochloric acid in that solution. Okay, so all this is if I could go back in my stock room and I have pellets of this that get dissolved in water, and then we fill it up to a certain volume and create our solution. So you use this math whenever we get to that part to figure out how many grams of the solid do I need to dissolve in 1 liter of water to make this certain concentrations. And you hopefully have noticed if you've been virtual the whole year, or if you're just watching this, you missed class, hopefully you've noticed that in some of the labs, we've used some of these solutions kind of over and over, but in different concentrations. Earlier in the year, we used a 0.5 molar hydrochloric acid, and then just recently in class, we used a 3 molar hydrochloric acid. That was much, much more concentrated, so it's kind of part of the reason why I left it for later in the year, so you guys were kind of used to using that stuff. Another just kind of daily example you might recognize or be more familiar with is like iced tea, right? So think about sweet tea. Some people don't like tea at all, or some people don't like sweet tea, but some people like it really sweet, right? So when you're making your sweet tea, if you want it to have exactly the same sweetness every single time, or let's say you work at Arby's or McDonald's or wherever you're working that they actually brew their own tea, you have to put in the same amount of sugar into the same volume of liquid every time to get the same taste. So that's technically the molarity of it. So if you knew how many grams of sugar you put into the tea solvent, you could calculate the molarity. So obviously if you want a higher molar, so if you want sweeter tea, you would put in more sugar or less sugar depending on your taste. Okay, so here's molarity. Molarity is the number of moles of the solute in 1 liter of solution. Okay, so with that, we know that we can calculate grams to moles. We can go like mass to moles, we can go moles to mass. That's just simple stoichiometry problem. So we're going to use a little bit of that stoichiometry, just the basic version of it, to be figuring out how many moles we need, because most of the time you're going to start with a mass, or you might be starting with the moles and need to figure out how much you need to put in. So this example just kind of goes through the process of that. Your molar mass is dissolved in enough water to make exactly 1 liter of solution. So you need to first find the mass that you're going to be dissolving. You're going to calculate that. I'm going to show you those equations in a second. So you would calculate the mass of solute needed to produce whatever molarity solution you need. So you would weigh that out. You put that in your volumetric flask. If it needs to be dissolved ahead of time, you can do that and then put it in just a little bit of water or whatever your solvent will be. And then you start filling it up. Okay, so this is just rinsing it out to make sure you get all the pieces, because that's important. And then you fill it up to this line. You probably have not come into contact with a volumetric flask very often or at all, but they all have this little line kind of towards the top. That is exactly 1 liter of a liquid will fit in there. So when you're making a certain molar solution, you have to put in your solute and then fill it up to the line. Okay, so it's basically, you're not adding 1 liter of water to it. You're just filling up the remainder of the volume with that amount of liquid. So I am always doing this like behind the scenes anytime that we are using a liquid in class. Most of the time I have already prepared that solution before class. So this is kind of what I'm doing before you guys get here. So the molarity is going to be the amount of solute in the volume of solution. So we just talked about that. It's moles per liter, and the unit you use for molarity is a capital M. Okay, so if you were going to prepare a 0.5 molar solution, you would first need to calculate the mass of solute needed. You would need to add a small amount of solvent into the solute to dissolve it. Then you would pour that into your volumetric flask and then fill that flask up with the solvent up to the 1 liter mark. Okay, so that's what I just talked about. This triangle just puts all of those little conversions together for you. We know that moles is going to be the mass divided by the molar mass. That's from stoichiometry. I've been using that a lot in the last couple of months, so hopefully you guys haven't forgotten that. But we also have this, right? So if we are trying to figure out, if I have the amount of moles and I need to know how many liters that's going to produce, you can divide this here with the molarity. So vice versa. So if you need to know the moles of the solute and you have the molarity in liters, you can multiply those. You guys know how this works. So depending on what you're looking for, you can use these relationships to solve for your missing variable. So here, I'm just going to kind of put this all up at one time. So this example, you have 3.5 liters of solution that contains 90 grams of sodium chloride. What is the molarity of the solution? And you do need to pay close attention to that, because molarity and molality are only different by 1 letter. So just make sure you're getting molarity when you're calculating this type of problem. So what do we have? What are we given? It tells us that the solute mass is 90 grams of sodium chloride. The solution volume is 3.5 liters. And it doesn't tell you that the solute is the sodium chloride, but you are assuming that you know that, right? Like we know that that's being dissolved in something. So your first step is to figure out the moles of sodium chloride. Okay, we have to have the moles to be able to divide the moles by the volume. So we're going to figure out our moles. You guys know how to do that. So I wrote it out like this, but it's also just a simple stoich problem, right? So you have your given mass divided by its molar mass, and that's that equal to 1 mole of whatever you're talking about. Doesn't matter. It all follows that path. And then you divide that to figure out that you have 1.54 moles of sodium chloride. Okay, so this 90 grams of sodium chloride is 1.54 moles. And then the molarity is just one more division portion. That's where you're going to use this triangle to kind of figure out which of these last steps you need to do. So molarity is always going to be the moles divided by the liters of solution. Okay, so we already know that our moles is going to be 1.54, and then it tells us up here that we have 3.5 liters of solution. So that's the volume we're going to divide it by. It's not always going to be 1, okay? So I know that when we were talking about the molarity of things and how to actually prepare a solution, you use 1 liter. But in these problems and in real life, you're not always going to have a situation where when you're trying to figure out what the molarity is, it's not always going to be 1 liter of solution. So in this case, we figured out the moles of our solute. We put that down here and divided it by the volume of the total solution. Okay, so it's the moles of the solute divided by the volume of the solution. That's going to equal 0.440 molar sodium chloride. Okay, so when you see this capital M, that's saying molarity, and that's saying that this is the concentration of that solution. So this being pretty low, you would say that's pretty dilute. The highest molarity you're going to get is 12 molar, and that's usually a stock solution. Like that would be what you would order if you were working in a lab. You would order that to use in your experiments, or I mean that's what we order at the school is stock bottles, and then we dilute it as needed. So another example, and this is looking at it from a different direction, okay? So to produce 40 grams of silver chromate, you will need at least 23.4 grams of potassium chromate in solution as a reactant. Okay, so this 40 grams of silver chromate is just extra information right now. Okay, so it's telling us we need 23.4 grams of the potassium chromate as our reactant. It has to be that much. All you have on hand is 5 liters of a 6 molar potassium chromate solution. What volume of this solution are you going to need in order to get 23.4 grams of the potassium chromate that you need in the solution? Okay, so this time we're trying to calculate the volume instead of the molarity. So given, again, we know that our volume is 5 liters because that's what this is saying. All we have is a 5 liter container of this 6 molar solution. Molarity is 6. Mass of our solute is 23.4 grams of the potassium chromate. Okay, and I cross this out because the mass of the product, we don't need that in this question at all. It's just there. So just be aware of that. Sometimes you'll have an extra value that you don't need to use. So here again, we have to find the moles because we have the mass, right? And again, you could work backwards. If you were trying to find something different and you were given the moles, you could use the moles to find the mass. There's multiple ways to work this, the same way it's kind of been all year with stoichiometry. So here we're finding the moles of the potassium chromate. Okay, so we did that the same way we did on the other one. We start out with the solute, the mass of the solute that we have, divided by its molar mass, which I just added these up on your periodic table, and that's equal to 1 mole. So we have 0.12 moles of potassium chromate. Now we need to figure out the volume. So this one's just going to be a little different. So if you look at that triangle in the bottom, we know that the volume is going to be equal to the moles divided by the molarity. So here, that's all we've done. So I have the moles of our solute that we just calculated divided by the molarity of the solution that it's in. So we have a 0.12 moles of potassium chromate divided by 6 molar potassium chromate is going to tell us that we only need 0.02 liters of this solution in order to make this reaction happen. So by using 0.02 liters of potassium chromate solution of this particular 6 molar solution, you're only going to need that much to get 23.4 grams of the potassium chromate to use as your reaction. So this goes back to limiting reactants and how much product you're going to produce and all of that, in that you're going to need a certain amount, a certain mass in order to fully produce this much of this product. So that's like one additional step is what this is. So we know we have this mass, but if you only have a solution of it and you don't have a solid sample of it, you're going to have to figure out what volume you need to be the equivalent of that mass. Hopefully that makes sense. So if you were doing a limiting reactants type of problem and you needed to know how much how many liters am I going to need to make this much solvent, or sorry, this much solute to react to produce this much. This is how you would follow that process. Last thing to talk about is molality. So molality, like I said, it's very similar sounding and looking on paper to molarity, but it's different. So molality is the concentration of a solution expressed in moles of solute per kilogram of solvent. Okay, so this is a little different. So we're looking at the solvent used, the mass of the solvent, to the moles of the solute. So I put these two on here to kind of just so you can see a good comparison. So for example, a solution that contains 1 mole of solute dissolved in exactly 1 kilogram of solvent is a 1 molal solution. Okay, so your symbol for molality is a lowercase m. If you are more comfortable just saying molal after it, like 1 molal solution, that's fine, because if you're handwriting this, it will be difficult for me to differentiate probably between your capital and lowercase m's. If you're typing it, it's not an issue. But also, if you're looking back on this later, trying to study for the final or whatever, you might look at this and be like, I don't know what I was calculating here. So I would just write out this entire word. Okay, so concentrations are going to be expressed in molalities when you're looking at properties of solutions related to vapor pressure and temperature changes. So molality is not going to be affected by changes in temperature, where molarity can be, because we know from our gases unit that if we're changing the temperature or the pressure, the volume is directly affected by that. So if the temperature or pressure will be changing during your experiment, you would not want to be using the molarity, because that's going to change the amount of solute you have in your compared to your solution. Molality is always the same. Okay, so this is an example of that here. So you have your molarity here. On a cold day, on a warm day, you know that the volume, it's going to expand. So even if it expands just very small, like a 1%, it's still changing your molarity. You see that down here? So it's 5 molar versus 4.95. And it doesn't seem like it would be a big deal, but it can be if you're working with something that is very reactive. You need it to be exact. So on the other side of this is looking at molality. Cold day versus warm day, the temperature really doesn't have any effect on the molality, right? So here you have 5 moles per 1 kilogram of solvent. It's still going to be a 5 molal solution. And over here, even though the volume has expanded, it's still 1 kilogram of solvent. Okay, because the volume expanded, all that means is it spread apart a little bit. It has more energy in it, so it's moving around more, so it takes up more space. But it still has the same mass, so it's 5 moles per 1 kilogram of solvent, which is still a 5 molal solution. So that's the difference between molarity and molality, and the why. Like, why are these two things both necessary to know? So that's why. So here's an example of a molality problem. So a solution was prepared by dissolving 17.1 grams of sucrose, which is table sugar, in 125 grams of water. Find the molal concentration of this solution. Okay, so we know that the molal concentration is going to be moles per kilograms. So moles of solute versus moles of the solvent, or sorry, kilograms of the solvent. So what do we have? We have the mass of the solute, which is 17.1 grams. We have the mass of the solvent, which is 125 grams. We have to put this in kilograms, so I've already converted it here. So we have 0.125 kilograms of water. So the first thing we have to do, again, is find the moles. Okay, same process as the others. So we're starting with the 17.1 grams of table sugar, and we're going to divide that by its mass. So we start with this sample size, dividing it by its molar mass, which again, we're just getting this all from the periodic table, set equal to 1 mole. So we're going to have 0.05 moles of sucrose. Now we have to find the molality. We know that the molality is just going to be the moles of our solute divided by the mass of our solvent. So we're putting that in down here. So I have 0.05 moles of sucrose divided by 0.125 kilograms of water. That's going to give us a 0.4 molal solution of sucrose. Okay, so then this information could be used to work with in your lab. You can use that value to calculate like what your products are going to be and all of that. So we know now how much we have to work with, or what concentration it is, and then we can go from there. So that is the usefulness of molarity and molality, because you're figuring out how much of a substance you have in this solution. So just because something's dissolved doesn't mean that it's the same as another container that is also dissolved with the same solute. So you guys do have 2 assignments today. So I'm going to kind of go back here. Let's see. Let's go back to our solubility. Nope. Oh, I'm way far away now. Here we are. Molarity. Okay. So these 2 formulas here are going to be kind of, kind of your home base, right? So you're going to always be going back to these for the very final step. Keep in mind that you are going to have to figure out how many moles you have first in most cases, unless it gives you moles. And that you can also use these in other formats. So if I have, let's just go back, all the way back to this one. So for molarity, you can solve for any of these 3 values. Okay, so depending on what the question is asking, you need to look at these relationships and figure out how you can use what you have to solve for any of these 3 variables. Okay, so there's a little bit of variability in there, and I know that makes some of you a little uncomfortable, but you need to use your analysis skills to kind of look at what you have, look at what you need, and figure out the steps to get from point A to point B, because there will not be a exact pathway every single time. It's similar to stoichiometry in that aspect. So you guys have 2 things. So you have an assignment that has some molarity questions to solve, just a lot of good practice. And then you also have a lab. So for the virtual students, your lab, it's exactly the same thing we're doing in class, but there's a video available for you to watch, and it shows the whole lab on video. I think it's like 6 minutes long. And the person who made this video did an excellent job of going through every single molarity question and like showing it written out. So if you are still a little stuck on this, not understanding, watch that video, the whole thing. He does all of the examples and shows you exactly how to do them. So like on paper. So if you have any questions, please let me know, and I hope you guys have a great day.